In this playlist, we're going to go through Hibbeler's statics textbook. So Engineering Mechanics Statics by Hibbeler. And in this video, we're going to flip through Chapter 1. So Chapter 1, General Principles. It starts by talking about mechanics. It says mechanics is a branch of the physical sciences that is concerned with the state of rest or motion of bodies that are subjected to the action of forces. So systems of forces, systems where forces are applied to solid, liquid, or gas bodies, and you're analyzing how and why the bodies react to the forces. That's mechanics. In general, mechanics can be subdivided into three branches: rigid body mechanics, deformable body mechanics, and fluid mechanics. So rigid body mechanics, that's statics and dynamics. All of the bodies that you analyze, the bodies that have forces applied to them, all of those bodies you consider to be rigid bodies. And we'll talk about what a rigid body is soon. Deformable body mechanics, that's like mechanics of materials. So the body is not rigid, but it's deformable. In fluid mechanics, you're analyzing forces that act on liquid or gas systems, liquid or gas bodies. So for example, pumping oil through an oil pipeline. You apply forces to the oil to push the oil through the pipeline, forces in the form of pressure. When you think about forces on fluids, you're thinking about pressure. A pump or series of pumps push the oil through the pipeline by applying pressure to it. And so in a similar way, if you have like natural gas, you apply pressure to the gas to push it through the pipelines with a compressor. Okay, rigid body mechanics is divided into two areas, statics and dynamics. Statics deals with the equilibrium of bodies, that is, those that are either at rest or move with a constant velocity, whereas dynamics is concerned with the accelerated motion of bodies. So in statics, we're analyzing force systems on solid bodies that are either moving with constant velocity or at rest. In other words, they aren't accelerating. Dynamics deals with forces on bodies that are accelerating. Those forces are causing the solid body to accelerate. So next, it goes into some history. It says the subject of statics developed very early in history because its principles can be formulated simply from measurements of geometry and force. For example, the writings of Archimedes in 287 to 212 BC deal with the principle of the lever. Studies of the pulley, inclined plane, and wrench are also recorded in ancient writings, at a time when the requirements for engineering were limited primarily to building construction. So building construction, you're designing buildings that don't move. They're in equilibrium. They're not accelerating. You don't want a building to move. And so as we solve statics problems in this playlist, you're going to notice that, so we've got a body, we have some known forces, and we're trying to solve for all of the unknown forces. And to do that, we're really just using geometry principles, lengths, angles, things like that. And so that's why they say that statics was developed much sooner than dynamics, because it says since the principles of dynamics depend upon an accurate measurement of time, this subject developed much later. Right? To study forces that cause acceleration, you need to accurately measure the acceleration. Galileo Galilei in the late 1500s, early 1600s, was one of the first major contributors to this field. His work consisted of experiments using pendulums and falling bodies. So I'm assuming the pendulums were to measure time. The most significant contributions in dynamics, however, were made by Isaac Newton in the late 1600s, early 1700s, who is noted for his formulation of the three fundamental laws of motion and the law of universal gravitational attraction. Yeah, so in the year 2023, mechanics still uses Newton's laws of motion as the foundation. Everything we're going to learn in this book, in this course, the foundation of it is Newton's laws. Shortly after these laws were postulated, important techniques for their application were developed by such notables as Euler, D'Alembert, Lagrange, and others. So yeah, since Newton, people have come up with useful ways to apply Newton's laws. Okay, fundamental concepts, basic quantities, length, time, mass, force. I've got a full video on units and measurement. We go into depth on quantities, the basic quantities. I'll post a link to that video in the description. Or if you're going through the playlist, that video should be just after or just before this video. Models or idealizations are used in mechanics in order to simplify application of the theory. Here we will consider three important idealizations. So, simplifying assumptions are very important in engineering. A quality engineer knows how and when to make simplifying assumptions. If there's any way that you can simplify your problem without too much compromise in the accuracy of the result you need, then you want to do that. And so in statics, these are three of the main simplifying assumptions that we use. As we saw earlier, statics and dynamics are a branch of rigid body mechanics. And so in this course and in dynamics, pretty much every solid body that we're analyzing, we're assuming is a rigid body. What is a rigid body? A rigid body can be considered as a combination of a large number of particles in which all the particles remain at a fixed distance from one another, both before and after applying a load. So what is that saying? That's saying that you're assuming the body doesn't deform, even when the load is applied to it. This model is important because the body's shape does not change when a load is applied, and so we do not have to consider the type of material from which the body is made. In most cases, the actual deformations occurring in structures, machines, mechanisms, and the like are relatively small, and the rigid body assumption is suitable for analysis. So yeah, every single material, no matter what it is, deforms when a load is applied to it. Even the stiffest materials we know of, like diamond, deform some amount when a load is applied to them. But like if we come back to page 1 and take a look at this picture here. For statics and dynamics problems, we're taking a look at a solid body as a whole and analyzing all of the forces on the body as a whole. So for example, if we wanted to analyze the forces on this pipe here as a result of being lifted, maybe we want to solve for the forces in these cables. And you could model the weight of the pipe acting at the center of mass of the pipe downward. Technically, the pipe is deforming due to its weight. So if you zoomed in at a very small scale, you would see that the pipe is deforming under its own weight. Kind of like that. I could exaggerate it even more. But for the case of a statics problem or a dynamics problem, you can just look visually at this. Before the pipe is lifted, it's straight across left and right. And after the pipe is lifted, it's still straight across left and right. So the idea is, for the sake of finding these forces, right, we know the weights. Let's say we're trying to find these forces. We don't need to say, well, before loading, so right when these cables become taut, they're about to lift the pipe, you've got this triangular configuration. And then once you lift the pipe up, these forces deflect in, 1/1000th of a degree. And that would be for this material, this type of iron or steel or cast iron or steel. For another material, they would deflect in 2/1000ths of a degree because materials deflect differently under loads. That would overcomplicate the problem, and the extra information you would get in your answer is negligible. It's a perfectly good assumption to just say that this is the shape right before loading. So right when the cables become taut and it's about to lift the pipe, this is the shape of the forces. And after lifting the pipe, it's the same shape, right? You're assuming the pipe doesn't deform under the load for the sake of the static analysis. I want to make that clear. In some situations, you can't assume that, but these assumptions are unique for each problem that's being solved, right? So like this long beam here, let's say this is lifting an even larger load than this, a really large load for this crane. Well, before the load is lifted, the beam is unloaded or under the load of its own weight. And after it's lifted, do you see the beam all of a sudden deform like this? Technically, if you zoom in very close, that's what the beam is doing. It is deforming like that. But for the sake of finding, the moment load and the vertical and horizontal loads that are holding the beam and the loads here, for the sake of finding all those loads, you don't need to consider how the lines of actions of these loads change because of that small beam deflection after lifting the load. That would be completely unnecessary. You would be getting differences in your final answer of, 0.00000 something percent. So there's no need to add that complication. So that's the rigid body simplification. In statics and dynamics, in rigid body mechanics, we're assuming that for the specific problems that we're solving, these assumptions are unique for each problem. The body is not deforming after the load is applied to it. And we're going to use this assumption on pretty much every problem. Unless stated otherwise, we're assuming that any body we're analyzing is a rigid body. Okay, another assumption that we're going to use is the particle assumption. Now, this is different from the rigid body assumption. We're not going to be using this on every single problem. This will only be in certain situations that will assume that a body is a particle. Okay, a particle has a mass, but a size that can be neglected. For example, the size of the Earth is insignificant compared to the size of its orbit, and therefore the Earth can be modeled as a particle when studying its orbital motion. When a body is idealized as a particle, the principles of mechanics are reduced to a rather simplified form, since the geometry of the body will not be involved in the analysis of the problem. So that's the key. If you're assuming that the body you're analyzing is a particle, then that's convenient because the geometry of the body is not involved in the analysis of the problem. That's very convenient. That really simplifies the problem. So the particle assumption, you have a point, and you're saying that all of the mass of the body is at that point, is concentrated at that point. So it still has a weight, right? This particle, this point has a weight, and then forces can act at that point as well. You can still have forces, known and unknown forces, and you can solve for those unknown forces. So it talked about the orbital of the Earth. What they're saying is you might consider this to be the Earth. And so I'm not an astrophysicist, but I guess the idea is, so the diameter of the Earth is a tiny percentage of the diameter or the major and minor axis of this ellipse. But even more than that, you might assume that, well, does the spin of the Earth, the momentum of the Earth's spin, does that affect the path? And I guess because the sun is so massive that everything is just dominated by the sun's gravitational pull, something like that, that even the Earth's spin means nothing as far as the shape of this orbital, right? You could say maybe, well, okay, the gravitational pull from the sun, it depends on distance, right? The gravitational pull from anything depends on distance from that object. So parts of the Earth that are a little bit farther away from the sun, because the Earth's diameter are getting pulled differently than parts close to the sun. But since the diameter of the Earth is so tiny compared to the distance from the sun, and also the sun is so massive that those differences in distance are completely negligible. So you see that the geometry of the Earth has no bearing on if you're analyzing the orbital motion, strictly for this problem. It might in another circumstance, but if you're just analyzing what is the orbital path of the Earth around the sun, the geometry is negligible. So you just model it as a point. All of its mass is concentrated at that point, and you've got like the force from the sun is acting on the point. You've got the velocity of the Earth is going in this direction. The Earth is accelerating towards the sun, but it has the velocity in this direction. And so you come up with a path. And if you considered factors like the fact that the Earth is spinning and so that affects the momentum or something, or the fact that certain parts of the Earth are a little bit further from the sun than other parts, then the difference you would get in the position of this orbital would be just completely negligible. So there's no need to consider the geometry of the Earth in this problem. If you're tracking an off-road vehicle, it might be completely okay based on the problem you're dealing with to model that vehicle as a particle. It has a mass, it has an acceleration, and so you just track its center of mass. So it's got a mass, and since you know its position at any point in time, you can find its acceleration at any point in time, because the derivative of position with respect to time is velocity, and then the derivative of velocity with respect to time is acceleration. But the idea is, for your problem, is there ever going to be a point where you have to consider the geometry of the vehicle, right? So like here's its acceleration, let's say, at any moment in time, this would change. For what situation would you need to consider the geometry of the vehicle? Well, okay, you've got air resistance, but I mean, just for analyzing it as it goes through the course, you can kind of look at the air resistance as just a force acting opposite to the direction that the particle is moving, right? And then the vehicle turning, like rotating about at the center of mass. I guess maybe if it's skidding or if it rolls over, but then now that's a different situation. You're assuming that the vehicle is going to go through the course in a normal sense. It's not going to be rolling. It's not going to be spinning, because that would mean that it's lost traction with the tires. So you can analyze, in general, what are the forces on the vehicle at any point in time, as long as the vehicle is going through the course in a normal way. Even if it's bouncing up and down, turning, going left to right, that's all just the center of mass accelerating. And then once you have those forces, then you could go to other problems where maybe you do consider the geometry. But for just analyzing in general the acceleration and the forces on the vehicle, you can model it as a particle. Okay? And so again, not every problem we're going to be able to model the body as a particle, and we'll talk about when you can and can't use the particle assumption in statics. Okay, the last simplifying assumption that we use frequently in this course is the concentrated force assumption. A concentrated force represents the effect of a loading which is assumed to act at a point on a body. Loading is assumed to act at a point on a body. We can represent a load by a concentrated force provided the area over which the load is applied is very small compared to the overall size of the body. The area over which the load is applied is very small compared to the overall size of the body. Okay, so we know that in the universe there's only two types of forces. So here's just a general body. This is like a 3D body, like a potato. Okay, there's only two types of forces in the universe. A force is going to be one of these two types. Either a body force. A body force is like gravity or magnetism or electrostatic force. That's those forces that seem to act through thin air. So you jump in the air and gravity with no contact just pulls you back down. The earth pulls you towards it with seemingly no contact. And it's called a body force because that force is uniformly distributed over every particle of the body in the same direction. So you can model that force as acting at the center of mass of the body. So this is like the weight of this. And it's the same idea with electricity or magnetism. Electrostatic force or magnetism doesn't have to act down towards the earth, but it's a body force that you can model at the center of mass. So you could put, this could be a magnetic force. If the force is not a body force, all other types of forces. So if the force is not a body force, then it's a surface force or a contact force. So it's transmitted via the contact between two bodies. Okay, so it's called a surface force because it's acting on the surface, over the surface. And it's coming from contact with another body. Now, every single surface force, no matter every single one in the universe, it acts over an area. Even if that area is very small, it's acting over an area. So it's like that entire force is distributed over an area, over the area of contact. So even if you have a sewing needle, if you're pushing a sewing needle into something, that seems like it's acting at a point, but no, it's just a very small area. It's still a distributed load technically. What the concentrated force assumption is saying is that if the area over which the load is applied is small compared to the overall size of the body, then you don't have to consider the load distribution. You can just say that force is acting at a point. Okay, this is strictly used for the type of problem that you're working. I want to stress that. Because stress is force divided by area. Okay? Stress is how we measure the strength of a material, how strong a material is, when a material is going to fail. Well, if the area is a point, then the stress is infinity. So if you're analyzing something regarding the strength of a material or the deformation of a material, you can't model a force at a point. That makes no sense. But like if we come back here, okay, I don't know what the connection is between these cables in the pipe. If there's like a hook or something or a shackle, there is some contact between this pipe and the cable, either directly or indirectly. I mean, it's going to be indirectly. Like you'll have the pipe and then some kind of hook, or maybe the cable's wrapped around the pipe. I don't know, but it's going to be an area of contact. Okay, there's some contact area that's pulling the pipe at this region in that direction. But for the sake of just finding the general force from these cables, the general force. So the statics problem would be like, you've got this force here, and then you're modeling the weight, the body force acting at the center of mass of the pipe. You model this as a point force. You don't consider the fact that this is technically a distributed load. This is like there's an area of contact here and there's a distributed load. That area of contact is small compared to the whole size of your problem. If you're just trying to find the load in the cables, the general load, you can model this as a point force with no problem. Now, let's say there was a shackle here. So you've got and the cable is attached to that shackle, and you're analyzing the shackle, right? So the cable, let's say, is hooked into the shackle, and then there's the cable. So if you're going to take away this hook and put a force here to represent the force from the hook on the shackle, well, maybe you do need to put this as a distributed load. Because the area now in relation to the size of the shackle, that area might not be small enough, or maybe it is. I mean, it just depends. You see, right? Maybe that needs to be a distributed load, and maybe you need to make this, the force on the pin here, a distributed load, or maybe you don't. It just depends. But like let's say this was a beam or something, and there was a crate sitting here. So there's a really heavy crate sitting here. Well, if the size of that crate is on a similar size of the beam, if this was a beam, well, it probably wouldn't be a good assumption for the problem to say that the entire weight of the beam is acting at the center of the beam, right? You would want to model that as a load. The load, that entire weight of that crate, is distributed over the contact area between the crate and the beam. They give an example here. So the force from the rail, the train rail on the wheel, on the wheel of the train. Again, there's no force that doesn't occur over an area. If it's not a body force, there's no contact or surface force that isn't occurring over an area. But can you model this as just a point force for the case of the static analysis? So you might be just analyzing a bunch of train cars, and so can you model those forces on the wheels as point forces? Well, yeah, definitely, because for the sake of your problem, is there any need to consider that as a distributed load? No, that area is so small, that contact area is so small compared to the overall size of your problem, even if you're just analyzing the wheel, right? So you've got a downward force from the load of the train car and an upward force here. You don't really need to consider the area. Now, does that mean that you're saying, if you do this, you're saying that, well, can I apply a point force here and the wheel won't fail? No, once you've solved for this force, let's say, if you want to analyze how the material is going to respond to that force, then you have a new problem. Okay, you have a new problem, and you zoom in and okay, here's the contact area between the wheel and the rail, right? It's like from here to here. Well, I know that, let's say you assume that the load distribution, it's like it does like this. It really peaks kind of at the middle, and it goes down. Well, like the area under that load, like if you integrate and find the net load, you know the net load is that load that you solved for in the statics or dynamics problem. But if you're analyzing like the deformation of the material, you know the net load. So you'll have to like assume a load distribution and analyze it from there. So it depends on these assumptions depend on the problem. If you were analyzing how this material in this region responds to the load, like how the material deforms in response to the load, you can't do a point force because now you're getting into stresses, forces over areas. That makes no sense. But for the case of solving for the general loads, like in a statics or dynamics problem, as long as that area of contact is small, you don't have to worry about it for that problem. And so we'll see in this course when we're using that point force assumption. So next it talks about Newton's laws of motion. I've got a full video that goes into detail on all three of Newton's laws. I'll post a link to that in the description. But if you're going through the playlist, that video should be right before or after this video. So in mechanics in the year 2023, so in this textbook, all three of these laws are the foundation of what we're doing, but you're probably most familiar with the F is equal to ma, the second law. And so in statics, every problem that we do, we're saying that the net result of the forces on something equals zero. They equal zero because the acceleration, the body isn't accelerating. And in most cases, the body isn't accelerating because it's at rest, like a building, right? It's at rest, not moving with constant velocity. And so that's how we know that something is not going to move, because the net resultant sum of all of the forces along the x, y, and z axis, as well as rotations about those axes, is zero. Okay, Newton's law of gravitational attraction, we still use this today. This is how we determine the weight of something. And I've got another video that goes into detail on this, on Newton's law of gravitational attraction and how that relates to what we use to calculate weight. I'll post a link to that video in the description as well. Okay, units of measurement, SI units, US customary. Check out the link to the units and measurement video in the description. Go into full detail on this, on all of this. Dimensional homogeneity, significant figures, rounding off numbers. All of these deserve their own separate video. I'll post a link. There's a video on significant figures, rounding. All of the links to all of those videos are posted in the description, or they're going to be in the playlist for you to watch before we get deeper into this textbook. So you need to watch those videos first. All right, and that's it for chapter 1.